Okay, so thanks everybody who's here for this afternoon talk. I know lunch was delicious and you're all probably looking forward to a nap at some point. I want to point out that most of the heavy lifting for this project has been done by an undergrad in our lab, James Shuttlecotty. He does fantastic work, and a lot of this is thanks to him. So on the present Earth, we have about 21% oxygen and about 1 part per million methane. And this is a direct result of life on Earth. Oxygen as a biosignature, then, is this grand idea that the microbial community can dramatically alter the atmosphere of a planet just over fairly short timescales in Earth's history. And this idea traces back to Lovelock in the 60s, as Eugenio mentioned, where he first posited that we could look for oxygen in combination with hydrocarbons. So for example, in the modern Earth's atmosphere, we have oxygen and methane as a biosignature for life on another planet. And not to poke fun at Daniel, but the habitable zone is a really great place to look for life because it's on the surface and it's modifying the atmosphere. And in conjunction with that, it's also much easier to get photons from a habitable zone planet than it is from a moon around a Jupiter. So terrestrial planets in the habitable zone are a great place to look for life. As I said, Lovelock pioneered this in the 60s, and it's been modified and updated throughout time. We figured out that while oxygen is a great tracer for life, ozone is a tracer for oxygen, and we can use that in place of that. There's a much larger spectral fingerprint for ozone. And so it's evolved from oxygen to ozone, and then ozone in combination with those reducing compounds that we talked about before. Now, another reason why we're looking for biosignatures on terrestrial planets in the habitable zone is because of our neighbors. So early in the solar system history, when Venus was getting pummeled by radiation from the sun, it underwent a runaway greenhouse, and most of its water vapor got into the upper atmosphere, was dissociated, and the hydrogen subsequently lost to space. That hydrogen loss, as Daniel mentioned, can trigger the buildup of oxygen in an atmosphere that's not related to life. If you lose an ocean of water from Venus, you can get up to 240 bars of molecular oxygen just from that ocean by losing all the hydrogen. So on the interior of the habitable zone, towards a sun-like star, you could destroy a planet but still get a transient oxygen signal. On the exterior of the habitable zone, our smaller cousin Mars currently has 0.2% of molecular oxygen in its atmosphere. This is a big deal. If Mars was slightly larger, it would have held on to more of its oxygen. And subsequently, Mars would look like a biological planet in terms of oxygen. So that we would have to look for these secondary signposts, these reducing compounds in conjunction with these oxidizing compounds to disentangle what processes are happening in that atmosphere. And so the habitable zone for terrestrial mass planets is the place to look for biosignatures. And that's why using oxygen as a biosignature for terrestrial mass planets is such a big deal. It's here where we find that life is the cause of oxygen buildup in the atmosphere, not anything else. Or that's what we hope anyway. In this study, we're employing a one-dimensional, horizontally averaged photochemical model. Like Eugenio mentioned, the casting group has had numerous versions of this code, but it essentially boils down to tens of kilometers tall test tube where photons come in the top and we have volcanic gases and rain out moving chemicals at the bottom of the atmosphere. And in the middle, we have a steady state chemical disequilibrium that's caused by the fluxes in and out of our atmosphere. And so for the runs I'm going to talk about today, we're in a 90% CO2 atmosphere, so it's going to be moved towards the outer edge of the habitable zone. Otherwise, it's going to be a little too warm and go into a runaway. In a 1 bar atmosphere, and our base case volcanism, we're putting out sort of the upper end of what we think of a terrestrial mass planet's volcanism. So we're putting out hydrogen and methane and hydrogen sulfide. And then when we reduce volcanic outgassing, we're just leaving in H2S, which is commensurate with what some of the more recent results for oxygen false positives have pointed out as being an initiator for their runaway oxygenation. So just to give you guys a little background, I'm going to talk about redox because that's what I do. So we define a system of redox with these neutral species that things are moving towards. Other chemical species are being pushed towards the redox neutral species. So in our case, we define neutral as water, CO2, and SO2. And so, for example, a reduced chemical species like methane, when combined with water vapor, gets you back to CO2, which is one of our other neutral species, but gets you an excess of hydrogen. And so the reducing species give you hydrogen in the redox budget. On the other end of things, the oxidized species like hydrogen peroxide, you have to add hydrogen to get them back to that base redox neutral species. And so in this case, hydrogen peroxide has a net -1 H2 molecule. So just for some audience participation, who knows what the redox number for H2SO4 is? Can you do the math in your head? Anybody? What's that? H2SO4? Well, so I guess I should explain this a little better. So you're going to take H2SO4 and you're going to add either hydrogen or one of the redox neutral species, and either you're going to evolve hydrogen or get back to the neutral species. So just to skip to the punchline, H2SO4 is a net -1 hydrogen, and then CO is a net plus a half hydrogen, or plus 1 hydrogen. See, even I can't keep it straight. So this is our model. Like I said, we have a big test tube where we're putting volcanic gases into the bottom of the model, and we assume that there's an ocean covering this planet that's only really in one dimension. We're working on that. So you have volcanic gases that are being evolved out of the subsurface, essentially, through the ocean layer and into the atmosphere. You have rainout of reducing species and oxidizing species that accounts for redox at the ocean-atmosphere boundary. And then you have the escape of reducing species out the top of the atmosphere. Now, on long time scales, the influx of volcanic gases, which are consistently reducing, so we have methane and hydrogen sulfide and H2 that are being evolved into the atmosphere. On long time scales, the volcanic gases are balanced by hydrogen escape. And so what's happening in the atmosphere-ocean boundary is important, but it's not the principal control on atmospheric redox on long time scales. And so what I'm going to do now is I'm going to show you a really scary table. And I'm going to point out that here, where who at all have no hydrogen emission, where they have a prodigious amount of oxygen, it's about 0.1% at the lower boundary, they have an imbalance in the fluxes of reducing components and oxidizing components at the atmosphere-ocean boundary. But if you were to look at the fluxes of hydrogen here, hydrogen, H2 and H, compared to the fluxes of H2S, which is their volcanic constituent, the volcanic component is much larger than the escape of hydrogen to space. So they should be gaining hydrogen in their atmosphere. Their atmosphere should be becoming more reducing with time, not more oxidizing. And so the fact that this lower boundary is not balanced is a problem, and a problem that we can fix by returning that hydrogen, returning that imbalance to the atmosphere. And so balancing the atmosphere-ocean redox budget is a key component of understanding the integrated redox state of these atmospheres. So I mentioned solar-type stars and how we have false positives around the habitable zone, but not in it. We haven't seen a conclusive case of a total atmosphere-ocean redox system that's been balanced that generates an oxygen false positive. The 2012 results from Renyu Hu et al. Are indicative of an imbalance at the ocean-atmosphere boundary, but not indicative of a false positive in the context of an atmosphere-ocean system that's totally balanced. But we have to look at other stars as well. We're not just going to look at terrestrial mass planets in the habitable zone of solar-type stars. We're going to look around M stars and K stars because they're just easier to observe habitable zone planets around. And so here, for my model results, I have the sun in green. I apologize for those of you who are red-green colorblind. I did try to make this as friendly as possible. But the sun is in green. We have HD 22049, which is a K2 star, so that's slightly less massive than the sun. And then we have two M dwarfs. We have AD Leo, which is a classic, very active M star that flares occasionally. It's pretty exciting for any planets that might be around it. And then we have GJ 876, which is a slightly less massive, slightly cooler M star in red here. And so if we were to take these stars with the same atmospheric parameters, the same fluxes of gases, the same parameterization of rainout, and do model runs, I'm going to show you a really scary figure with lots of lines, but just stick with me. So we see that for major constituents like water vapor and CO in the base case, which is the left-hand side, so remember we're getting more volcanic outgassing in the left-hand cases, your left, not mine, you get pretty consistent atmospheric profiles across different stellar types. But it's really when you get down here to where we're looking at the oxygen-bearing species that something stands out. And so here, around GJ 876, we get about 10 to the minus 7 oxygen at the lower boundary, which is somewhere between 6 and 10 orders of magnitude more oxygen than every other star in our model. Excuse me. So this is just the base case where we have lots of volcanic outgassing, lots of reducing power going into the atmosphere. If we turn down the volcanism, not turn it all the way off, just turn it down to a minimal level, we're still putting reducing compounds into the atmosphere, you get something like we see on Mars, where we're nearly at 0.1% oxygen at the lower boundary. And this is a big deal. If you were to continue to turn down volcanism on a terrestrial mass planet in the habitable zone, you would get a runaway oxygenation. You would get this false positive around an M dwarf, which is probably where we are going to find our first terrestrial mass planet, where we're going to do our first spectroscopy, where we're going to find this signpost that we think is infallible. And so this result here is preliminary. I won't say it's conclusive, but it is indicative that there's a lot of work to be done on understanding how M dwarfs, how the spectral fluxes affect atmospheres, especially in the context of biosignatures. So we find this false positive lurking for high CO2 atmospheres. Future work, we're going to look into actually keeping track of aqueous chemistry. Currently, we're just returning reducing power to the atmosphere as hydrogen. It's not the best, but we don't have a firm grasp on what aqueous chemistry is going to look like on an alien world. So future work also will include exploring what parts of the stellar radiation are influencing this oxygen false positive. So if we turn down, for example, the far UV radiation or the near UV radiation, what's going to cause us to build up oxygen? Because every star is not alike. And so we need to understand where in the stellar parameter space we're going to find these planets that look like they have life, but probably don't. And so with that, I'm going to finish and take questions.
Yeah, thanks, Chester. So,
no one cares about you, Eric.
Thanks, Sonny.
Yeah.
If you go back to your figures, your 4 figures slide, what's the main constituent of your atmosphere? Is it N2?
No, but these are 90% CO2 atmospheres, so N2 is a very minor component of these.
Okay. I see, and you don't plot CO2 here. Okay, cool.
Well, I mean, so we set CO2 as a fixed mixing ratio, and I mean, there have been studies that have used it as an actual variable chemical constituent, but there's not really much of a difference between, at these levels, whether it's a fixed mixing ratio or a variable chemical constituent.
Thanks.
I do have a quick question. So,
Sure.
From the observational side, what kind of telescopes do we need to observe stuff like that? Is that possible with James Webb or more with like next generation telescopes?
That's actually a really good question for Natasha. I think that the standard understanding is that a 0.1% oxygen is detectable with the next generation of telescopes. So the oxygen false positives we see for reduced volcanic outgassing could be a potential false positive.
Okay, let's thank him again.